Deep beneath the hills of South Dakota, in a town once powered by gold, something unprecedented is unfolding. It's not a mining operation or a subterranean military facility. It's a massive scientific undertaking that may answer one of the deepest and most puzzling questions ever posed by humanity. Why does anything exist at all? This isn't just a philosophical musing, it's a serious question in modern physics. One that touches on the very origin of the universe, and more specifically, the imbalance between matter and antimatter. To answer it, scientists from around the world, led by America's Fermilab, are building one of the most ambitious experiments ever conceived. It's called the Deep Underground Neutrino Experiment, or DUNE, and it might hold the key to solving one of the most fundamental mysteries in science. Why is there something instead of nothing? To understand the purpose behind DUNE, we first have to revisit what we think we know about the beginning of the universe. According to the standard model of physics, the Big Bang should have created equal amounts of matter and antimatter. Matter makes up everything we can touch, see, and interact with. Stars, planets, people, pizza. Antimatter is its mirror image, with the same mass but opposite charge. When matter and antimatter meet, they annihilate each other in a burst of pure energy. So if the early universe truly produced equal amounts of both, they should have canceled each other out completely, leaving behind nothing but energy, a vast, empty, glowing void. But that's not what happened. Instead, the universe tipped ever so slightly in favor of matter. For every 3 billion antimatter particles, there were 3,000,000,001 matter particles. That single extra particle in every 3 billion was just enough to seed the creation of everything we know: galaxies, solar systems, oceans, trees, and human consciousness itself. All of it exists because of that tiny imbalance, and yet no one knows where it came from. Why did the universe produce slightly more matter than antimatter? What mechanism tipped the scales? The ghost particle that could explain everything. For decades, physicists have searched for clues to explain why matter dominates the universe. One promising lead lies in the elusive neutrino, a nearly massless particle that passes through ordinary matter by the trillions every second. So elusive is the neutrino that it could travel through 5 light years of solid lead with only a 50% chance of being stopped. Despite their ghost-like nature, neutrinos might behave differently than their antimatter counterparts, a subtle difference that could explain the matter-antimatter imbalance. Detecting them, however, is incredibly difficult. That's why DUNE is being built deep underground, shielded from cosmic radiation, to give scientists a fighting chance at observing these mysterious particles in action. The scope of DUNE. The Deep Underground Neutrino Experiment is unlike any other science project in the world. It spans over 1,300 kilometers, stretching between 2 states, and consisting of 3 main facilities. It all starts just outside of Chicago, at Fermilab in Illinois. Here, engineers are building what will soon become the world's most powerful particle accelerator for neutrino production, called 𝐃𝐨𝐧'𝐿. This machine will accelerate protons to nearly the speed of light before slamming them into a fixed target. The resulting collision produces a beam of neutrinos, which will be focused and fired underground through the Earth. From there, the beam begins its journey west, eventually traveling more than 1,286 kilometers to reach the far detector, which is being built in the old Homestake gold mine in 𝐿EAD, South Dakota. A near detector, located just 600 meters from the source, will analyze the beam's characteristics shortly after its creation. This allows scientists to compare the beam at both ends of its journey and see how it has changed over time and distance. Why underground? Shielding the signals. Why is the beam fired underground? Because it's more efficient and shielded that way, and over such a long distance, the beam spreads out, like a flashlight beam projected across a field. That's why the far detector has to be much larger than the near one. It needs to capture enough neutrinos to be statistically significant. At its destination in 𝐿EAD, South Dakota, the detector is being installed nearly 1.5 kilometers beneath the surface, deep inside a decommissioned gold mine. The detector chambers themselves are housed within 3 massive caverns, each large enough to hold the Statue of Liberty laid flat 3 times over. Repurposing the Homestake mine. Converting the century-old Homestake gold mine into a modern science facility was a major engineering challenge. After its closure in 2002, much of the infrastructure had deteriorated. Engineers had to restore the hoist system, reinforce the historic headframe, and modernize the shaft, just wide enough to fit 2 shipping containers. Space was tight, so large equipment had to be disassembled above ground and rebuilt deep underground. Excavation involved using massive drill jumbos to bore into rock, followed by carefully placed explosives. explosives. Over time, this process removed 800,000 tons of rock. To keep the cavern stable at such depth, crews installed 20-foot bolts and steel mesh, creating a reinforced grid capable of withstanding the immense underground pressure. Engineering at the edge of possibility. Once excavation was complete in 2024, the process of turning the empty caverns into a working laboratory began. Concrete floors were poured, electrical systems were installed, and the chambers were lined with shotcrete to stabilize the surfaces. The middle cavern is being equipped with utility systems like cooling units and substations, while the north and south caverns will each house 2 of DUNE's 4 major neutrino detectors. And these detectors are extraordinary. Each one will be a liquid argon time projection chamber, or LRTPC, a marvel of modern engineering. Inside each chamber is a massive tank filled with ultra-pure liquid argon cooled to minus 184 degrees Celsius. When a neutrino finally collides with an argon atom, a rare but measurable event, it releases a spray of particles. These particles ionize the surrounding argon, creating tiny electric signals that can be captured by thin wire meshes stretched across the chamber. These meshes, made up of over 24 kilometers of wire, are sensitive enough to reconstruct a three-dimensional image of the interaction with millimeter-level precision. This level of detail allows researchers to analyze every neutrino event in stunning clarity, potentially revealing previously unknown behaviors or differences between matter and antimatter particles. Why DUNE outclasses its peers. Unlike other neutrino experiments like Japan's 𝐼𝐸𝐾𝐭, which relies on detecting faint flashes of light in giant water tanks, DUNE's liquid argon approach focuses on measuring electrical charge. This results in much higher resolution images, giving scientists a clearer look at the mechanics of each interaction. While 𝐼𝐸𝐾𝐭 detects collisions at the scale of centimeters, DUNE's detectors can observe them at the millimeter level, an enormous improvement in scientific terms. But building the detectors is only half the story. The data that DUNE produces will be enormous, and analyzing it requires equally powerful computers. That's why many of the project's partner institutions are investing in cutting-edge processing units and AI-supported platforms to sift through the information. With hundreds of billions of data points being collected, only high-performance computing, equipped with advanced neural processing units, will be able to make sense of it all. When will the discoveries begin? So what happens next? Full-scale operations aren't expected to begin until the early 2030s, possibly around 2032. At that point, Fermilab's accelerator will fire alternating beams of neutrinos and antineutrinos toward the detectors in South Dakota. Scientists will compare the behavior of both types to look for differences. If even a tiny asymmetry is observed, it could explain the imbalance between matter and antimatter in the early universe. If no difference is found, it would suggest that the mystery remains unsolved, and we'll need new physics to explain our existence. And that's the incredible story of DUNE, the giant underground lab that might just unlock the secrets of the universe. If you found this fascinating and want to see more videos about epic science projects, groundbreaking technology, and the future of discovery, make sure to give this video a thumbs up and subscribe to the channel.